So let's understand the two-body problem, the classical mechanics one. What do we know about the system and do we know about its solution?
Absolutely. The two-body problem in classical mechanics usually involves analyzing the motion of two masses interacting via some force like gravity or electrostatics. The key is that the system can be reduced to a single body problem by considering the relative coordinates. This means that we look at the center of mass and the relative position of the two bodies. And once we do that, the problem becomes more tractable, often leading to closed form solutions. Let me know if there's a specific aspect you'd like to dive deeper into.
So this when we decide that two-body properties or the parameters, we say that there are only two bodies that are interacting via some force. It may be gravity or electrostatics, but after that we say that they have mass, they might have charge, they might have its radius.
Exactly. We typically characterize each body by its mass, and if we're dealing with electrostatics, then we'd also consider their charges. Their radii or sizes can influence the interaction, especially if we're considering things like tidal forces or the distribution of charge. And all of these parameters help define the dynamics of the system and the nature of the force between them.
So, okay, the bodies are decided that we have to take two body and with their own its own properties. What about next? What is the dimension we are taking so that uh, I mean like playground where they can interact.
Great question. Usually we consider the system in three-dimensional space, since that's how we experience the physical world. In three dimensions, the bodies can move freely along the X, Y, and Z axes, and their interactions will depend on their relative positions in that 3D space. Of course, we can also consider special cases like reducing it to a two-dimensional plane if the movement is constrained, but generally, three dimensions give the most complete picture of their interaction.
Why do we consider 3D? Because it is like X, Y, Z axis. What about time?
Exactly, time is another crucial dimension. So, in classical mechanics, we typically consider the system in a four-dimensional framework. Three spatial dimensions, X, Y, Z, and one time dimension. The time dimension allows us to track how the positions and velocities of the bodies evolve. So, the complete description of their motion involves both their spatial coordinates and how these coordinates change over time. It's this combination that gives us a full picture of the dynamics.
So, capturing the full picture of dynamics means that okay, the playground it's set is like it's a 3D space with time also there, and then what next? Oh, they have mass and they are interacting via some force. So, the force will decide that how they will evolve in time.
Exactly, you've got it. The forces acting between the bodies determine how their positions and velocities change over time. That's where Newton's laws of motion come into play, and the equations of motion are derived from those forces. Over time, as we integrate these equations, we get the trajectories of each body in that 3D space. It's really the interplay of mass, force, and time that defines the dynamics of the system.
So mass, force, and time. But you mentioned about we solve this two body by considering single body, something like center of mass frame.
Yes, exactly. By shifting to the center of mass frame, we can simplify the problem. In that frame, the motion of the two body system reduces to the motion of the relative coordinate, and the center of mass itself moves as if it were a single particle. This approach effectively decouples the problem into two parts: the motion of the center of mass and the relative motion of the two bodies. This makes it much easier to analyze and solve, especially when dealing with gravitational or electrostatic forces.
Okay, can you tell me again what's the whole procedure to solve this two body problem?
Of course. So the general procedure involves a few key steps. First, you define the system by identifying the masses, the initial positions, and the initial velocities of the two bodies. Then you consider the forces acting between them, like gravitational or electrostatic forces, and write down the equations of motion using Newton's laws. Next, you shift to the center of mass frame, which helps simplify the problem. In that frame, you can separate the motion into the center of mass motion and the relative motion. After that, you solve the relative motion, often reducing it to a single effective particle moving under the combined potential. Finally, you integrate the equations of motion over time to get the trajectories of both bodies. And that's pretty much the overall process.
Okay, what does this trajectory tells about that dynamics of the body? What are the dynamics we observed at the end?
The trajectory essentially shows how each body moves through space over time. From the trajectory, we can observe several dynamics. For instance, we can see how the body's positions change relative to each other, how their velocities evolve, and how energy is conserved or exchanged. For example, in a gravitational two body problem, you might see elliptical orbits, circular orbits, or even hyperbolic trajectories depending on the energy and initial conditions. By analyzing these trajectories, we can understand the stability of the system, how the bodies interact, and how energy is transferred between them. It gives us a complete picture of the system's dynamics.
Okay, in this case,
No worries, take your time. If you have any specific scenario or detail you'd like to explore further, or if you want to dive into any particular aspects of the two body problem, just let me know. I'm here to help.
so these two bodies are there in the spatial plus time dimensional space, and then they interact via simple like two body problem. Uh, Earth and Sun interact via the gravitational force, and then we wrote down the kinetic energy and potential energy, and there we solve the Lagrangian and we get the dynamics in the sense of orbit.
Absolutely, you've got it. In that scenario, we consider the kinetic energy of each body, which depends on their masses and velocities, and the potential energy, which depends on the nature of the force. In the Earth Sun example, that would be gravitational potential energy. By combining these, we get the total energy of the system. Then, by applying Newton's laws, we derive the equations of motion and solve them, often leading to orbital paths like ellipses, circles, or hyperbolas. This approach gives us a clear understanding of the dynamics and how the bodies evolve over time in their orbital dance.
So we apply Newton's laws and derive equation of motion and solve them, leading to the orbital paths in this case.
Exactly. By applying Newton's laws, we get differential equations that describe how the bodies move under the influence of the forces. When we solve these equations, we can derive the specific orbital paths like elliptical orbits in the case of bound systems or hyperbolic trajectories for unbound systems. It's that process that helps us understand the shape, orientation, and evolution of the orbits in detail.
In this case, the Earth and the Sun case, how do we simplify the two body into one body?
In the Earth Sun system, we usually simplify by considering the center of mass, which in this case is very close to the center of the Sun because the Sun is so much more massive than the Earth. So we can treat the Sun as essentially stationary and focus on the Earth's motion around the Sun. Alternatively, we can also look at the problem from the Earth's frame and consider the Sun's motion as negligible. In practice, this means that we can approximate the Earth's orbit as being around a fixed point, and that makes the math and the understanding a lot simpler. Essentially, we're reducing the complexity by focusing on one body's motion relative to the other.
Okay, the things are going good. So I need one last intuition that uh, can you give the better picture how for the first time they have solved this two body problem?
Absolutely. The two body problem was first rigorously tackled in the context of celestial mechanics, especially with Kepler's laws, which Johannes Kepler formulated in the early 17th century. Kepler discovered that planets move in elliptical orbits with the sun at one focus, and that laid the groundwork. Then Isaac Newton came along in the late 17th century and unified Kepler's laws under the framework of his law of universal gravitation by applying Newton's second law of motion and his law of gravitation. He derived the equations of motion for the two body system. This allowed for a complete mathematical description of how two bodies interact under gravity, leading to the precise prediction of orbits. So the combination of Kepler's empirical observations and Newton's theoretical framework gave us the full picture of the two body problem as we know it today.
I can say that the dynamics is observed in the form of orbits here.
Absolutely, that's a perfect way to put it. The dynamics really manifest as the orbital patterns we observe, and each orbit gives us insights into the underlying forces and energy of the system. It's really fascinating how that interplay of mass, force, and energy all come together to create those elegant paths we see.
Okay, can you give conclusion what we have discussed till now?
Of course. To sum it up, we started with the concept of the two body problem, considering how two masses interact under forces like gravity or electrostatics. By moving to the center of mass frame, we simplified the problem, allowing us to focus on the relative motion. Then, by applying Newton's laws and the principle of conservation of energy, we derived the equations of motion and ended up with the orbital paths we observe, such as ellipses or hyperbolas. In essence, the dynamics of the system are fully captured in these orbital motions, and that's how we understand and predict their behavior. If you have any other questions or need more details, just let me know.
Okay, thank you.